Hello everyone and welcome back to Chemist Tea Time. In today's discussion, we'll be discussing calorimetry and how to use this technique to calculate enthalpy changes. Calorimetry is a technique used to calculate enthalpy changes for a chemical or physical process, and the device used are referred to as calorimeters. Some important terms that we need to define before moving forward are heat capacity, which is the amount of heat required to raise the temperature of an object by 1 degree Celsius, and is denoted by capital C and is calculated by heat divided by change in temperature, where specific heat of a substance is the amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius and is denoted by capital C subscript S and is calculated by heat divided by mass times the change in temperature. We can also express specific heat in respect to moles, which is known as the molar specific heat capacity, and is the amount of heat required to raise the temperature of 1 mole of substance by 1 degree Celsius, and is calculated in a similar manner. We can also rearrange these expressions to solve for heat, denoted by Q, for each of these expressions. It is important to note that the heat capacity is an extensive property, and its value is proportional to the amount of substance, whereas the specific heat capacity and molar specific heat capacity are intensive properties and are only dependent on the type of substance, not the amount. Here is a table of some common specific heat capacities at 25 degrees Celsius. It is important to point out that depending on the physical state of a substance, the specific heat differs, for example, water. Let's do a practice problem. Calculate the amount of heat that water absorbs when a flask containing 8.0 times 10 to the second grams of water is heated from 21 to 85 degrees Celsius. The specific heat capacity of water is 4.184 joules per gram degrees Celsius. In order to calculate the heat, we will use the rearranged equation that we showed previously, that Q is equal to the mass times specific heat capacity times the change in temperature. An easy way to remember this formula is that heat is equal to MCAT. Next, we plug in the values into the expression, and heat is equal to positive 2.1 times 10 to the 5 kilojoules. It is important to look at the sign of heat. In this case, Q is positive and means that as the temperature increased, the water absorbed the heat. As a reminder, the law of conservation of energy states that energy is not created nor destroyed and is transferred. Going back to our previous discussion where we discussed thermal equilibrium, when two objects at different temperatures are placed in contact with one another, heat flows from the higher temperature object to the cooler object until both objects reach the same temperature. We can express this process by the following equation. The heat of the cold object plus the heat of the hot object is equal to 0, which can be rearranged to Q cold is equal to the negative Q hot. As you can imagine, we can then substitute the new formula for calculating Q into this expression as follows. A calorimeter is a closed container and measures the heat that is exchanged from the system to the surroundings. Keep in mind, the system is a substance or substances undergoing a chemical or physical process, and the surroundings is everything else around it. We will first begin talking about constant pressure calorimetry. Keep in mind, if a reaction releases heat, Q of the reaction is less than 0. Then the heat is absorbed by the calorimeter and Qcal is greater than 0. This is also true for the reverse of that statement. The reaction absorbs heat from the surroundings and is greater than 0, and Qcal is less than 0. Keep in mind that in each scenario, the amount of heat absorbed is equal to the magnitude of heat released with the opposite sign. For a constant pressure calorimeter, the change in enthalpy is defined as the flow of energy at constant pressure. Reactions performed at constant atmospheric pressure can use a coffee cup calorimeter. This apparatus is insulated to reduce heat loss from the calorimeter to the environment. It also is equipped with a thermometer stirrer and is sealed. Let's walk through an example for a constant pressure calorimeter. When 5.03 grams of solid potassium hydroxide are dissolved in 100 milliliters of distilled water in a coffee cup calorimeter, the temperature of the liquid increases from 23 degrees Celsius to 34.7 degrees Celsius. The density of water in this temperature range averages 0.9969 grams per milliliter. What is the change in enthalpy of the solution in kilojoules per mole? Assume that the calorimeter absorbs a negligible amount of heat, and because of the large volume of water, the specific heat of the solution is the same as the specific heat of pure water, 4.184 joules per grams degrees Celsius. To calculate the enthalpy of the reaction, we will first need to calculate the Q-cal using the following expression. We have the specific heat and change in temperature. The only thing we need to calculate in this case is the mass. From the problem, they tell us 5.03 grams of KOH are dissolved in 100 milliliters of water. We need to convert the volume of water to grams using the density. We get 99.69 grams of water. Next, we plug everything into the heat formula to determine Q-cal, which is 5.13 kilojoules. However, we need to determine the enthalpy of the solution, which is equal to the negative of the heat of the calorimeter and is equal to negative 5.13 kilojoules and is an exothermic reaction. Next, the problem asks for our units to be in kilojoules per mole of KOH. This is done by calculating the moles of KOH and dividing it by the enthalpy, which is equal to negative 57.2 kilojoules per mole. However, in some cases, it is not feasible to do a constant pressure calorimeter, and instead a constant volume calorimeter is used and is known as a bomb calorimeter. A bomb calorimeter is an isolated system because there is no loss of mass or heat. The sample is placed in a bomb and filled with excess oxygen and placed inside an insulated container equipped with a fixed volume stirrer and thermometer. The stirrer is to ensure that the water is homogenized throughout the entire experiment. The sample is then ignited electrically and the heat released is absorbed by the bomb and the water. The heat released is measured by the change in temperature of the water. In this case, Q reaction is equal to the negative Q-cal. Remember, Q-cal is equal to the Q of the water plus the Q of the bomb. For a bomb calorimeter, it has its own heat capacity, denoted as capital C subscript cal. This is calculated by burning a known substance with a known heat combustion, and benzoic acid is often used. Once a specific heat of the calorimeter is determined, that calorimeter can be used to measure the heat of combustion for other substances. Because this reaction is constant volume and not constant pressure, the measured heat change corresponds to the change in internal energy rather than the change in enthalpy. Keep in mind the internal energy is equal to Q minus P delta V. If the change in volume is constant, this term becomes zero and the internal energy is equal to Q subscript V. However, the difference between the internal energy and enthalpy is a relatively small correction factor, and we will not concern ourselves with it for now. In today's discussion, we discussed calorimetry and how to use calorimetric data to calculate enthalpy changes. We also introduced two different calorimetry setups and how to use each in our calculations. Thank you for joining me today and have a wonderful day. Thank you.